A virtual power plant VPP is a network of distributed energy resources like photovoltaic PV systems, batteries, wind turbines, and electric vehicle EV chargers, aggregated and managed through advanced software to act as a single, coordinated entity. By pooling and optimizing these resources, a VPP provides flexibility to the energy grid, engaging in value streams such as frequency regulation, demand response, and energy trading. Its primary role is to enhance grid stability, maximize renewable energy integration, and create economic benefits for participants while supporting the transition to decentralized and sustainable energy systems. A virtual power plant VPP leveraging residential flexibilities requires interplay of multiple functions. By seamlessly integrating these components, the VPP not only enhances energy flexibility and grid stability but also maximizes the economic and environmental benefits of renewable energy systems. This coordinated functionality ensures that residential resources are optimally aggregated and dispatched to provide valuable grid services and market opportunities. Here are some of the key characteristics of virtual power plants: engaging customers, attracting and onboarding asset owners, such as those with solar PV systems, residential batteries or EV chargers, into the VPP network. Establishing agreements and contracts to ensure collaboration and seamless operation. Monitoring and managing assets, continuously tracking the performance and availability of distributed energy assets in real time. Enabling centralized control to ensure all assets function cohesively within the VPP. Coordinated aggregation, combining a variety of energy resources into a unified and well-coordinated system. Managing diverse assets to act as a single, optimized unit that maximizes flexibility and efficiency. Operational optimization, using advanced analytics and algorithms to determine the most efficient ways to use aggregated resources. Adapting operations in real time to meet energy demands, reduce costs, and balance supply-demand dynamics. Market integration, enabling participation in electricity markets such as the intraday market or imbalance market, enabling frequency regulation, demand response, and grid balancing. Acting as a bridge between distributed energy assets, market participants, and grid operators such as TSOs and DSOs. Financial management, handling billing and financial settlements for energy contributions and services provided by participants. Ensuring transparent and equitable distribution of revenue among asset owners and stakeholders. Types of virtual power plants, VPP, are classified based on the types of assets they aggregate and their operational goals. Supply-side VPPs, aggregate distributed energy resources such as solar PV systems, wind turbines, and small-scale hydroelectric plants. By coordinating these generation assets, supply-side VPPs can operate collectively as a single power plant, optimizing energy production and participating in wholesale energy markets. Additionally, they can provide services like capacity market mechanisms and strategic reserves, enhancing grid reliability. Demand-side VPPs focus on aggregating flexible consumer loads, including residential, commercial, and industrial energy consumers. By managing and adjusting these loads, VPPs can perform demand response activities, where consumers are financially rewarded for shifting or reducing consumption during peak demand periods. This approach helps balance supply and demand, providing value in intraday and day-ahead markets. Hybrid VPPs combine both supply-side resources and demand-side flexibilities, integrating generation assets like renewables with controllable loads and energy storage systems. This combination offers maximum operational flexibility, allowing hybrid VPPs to provide a wide range of grid services, including frequency containment reserve (FCR), automatic frequency restoration reserve (AFRR), and reactive power management. Moreover, hybrid VPPs can optimize their participation in wholesale energy markets, maximizing revenue potential by strategically responding to market opportunities and price signals. By participating in multiple value streams, VPPs enhance grid stability and facilitate the integration of renewable energy sources, contributing to a more resilient and sustainable energy system. Requirements for a successful virtual power plant VPP. For a virtual power plant to operate effectively and deliver its potential value, several critical factors are essential. These requirements can be broadly categorized into technical infrastructure, regulatory support, and favorable market conditions. Technical requirements, reliable monitoring and control systems, accurate and continuous monitoring of distributed energy resources is essential. Robust control systems, like home energy management systems (HEMS), ensure that assets are synchronized, can respond quickly to grid demands, and serve as the foundational building block for VPPs. Scalable and adaptable software. VPPs must utilize advanced software capable of optimizing operations in real time. This software should handle complex data streams, adapt to changing conditions, and scale seamlessly as more assets join the VPP. Hardware compatibility and communication protocols. Diverse assets, such as solar panels, batteries, EV chargers, and wind turbines, must integrate smoothly. Interoperability across various hardware manufacturers and communication protocols is critical to ensure all components work cohesively. Why is a virtual power plant important? VPPs play a pivotal role in revolutionizing the energy sector by leveraging distributed energy resources like solar panels, wind turbines, batteries, and electric vehicles. Here's why they are essential for the modern energy ecosystem: enabling the integration of renewables, bridging variability. VPPs effectively incorporate renewable energy sources into the grid by managing their intermittent nature, e.g., fluctuating solar or wind production. Maximizing renewable output. By aggregating and optimizing DERs, VPPs ensure renewable energy is utilized to its fullest potential, reducing curtailment and waste. Decarbonization. VPPs expedite the transition to cleaner energy by supporting higher penetration of renewables, contributing to global climate goals. Decentralizing energy systems. Empowering local generation. VPPs decentralize energy systems by enabling households and businesses to contribute to the grid, reducing reliance on centralized power plants. Prosumers in action. Homeowners with solar panels or batteries become prosumers, generating energy and participating in energy markets through VPPs. Enhanced resilience. Decentralized energy systems are more resilient to localized disruptions, providing a more reliable energy supply. Balancing supply and demand. Real-time adjustments. VPPs leverage advanced algorithms to align supply with demand in real time, ensuring efficient energy distribution. Demand response. They adjust consumption patterns by encouraging energy use during off-peak periods, alleviating stress on the grid. Market participation. VPPs facilitate access to energy markets, allowing aggregated assets to trade surplus energy or flexibility, generating revenue for participants. Addressing flexibility challenges. Congestion management. VPPs assist grid operators, TSOs and DSOs, in alleviating network congestion by intelligently managing distributed assets. Frequency stabilization. Through frequency regulation services like FCR or AFRR, VPPs maintain grid stability, which is crucial for preventing blackouts. Forecast error mitigation. VPPs minimize the impact of forecast errors by rapidly dispatching aggregated energy or flexibility to cover shortfalls or absorb excess generation. Driving economic efficiency, cost savings. By optimizing DERs, VPPs reduce the need for costly grid upgrades and the expansion of centralized power plant operations. Incentives for prosumers. Participants in VPPs benefit financially by trading energy and flexibility, making renewable energy investments more attractive. Supporting the energy transition. Scalability. VPPs can scale with the increasing deployment of DERs, making them a key enabler of the energy transition. Innovation. They pave the way for innovative energy technologies, such as smart meters, dynamic tariffs, and vehicle-to-grid V2G systems. Role of Energy Management Systems (EMS) in VPPs. An energy management system (EMS) is the core technology that drives the operations of virtual power plants (VPPs). Acting as the backbone of the system, the EMS ensures that distributed energy resources DERs are monitored, controlled, and optimized to deliver maximum value to the grid, market, and participants. Backbone of VPP operations. Centralized coordination. The EMS acts as the control hub for all distributed assets within the VPP. It oversees and integrates the operations of energy producers, consumers, and storage systems to function as a unified, flexible virtual power plant. Efficient energy distribution. By aggregating the capabilities of various assets, the EMS ensures that energy is delivered where it is needed most, in the most efficient and cost-effective manner. Real-time monitoring and control. Asset visibility. The EMS provides continuous, real-time monitoring of all DERs, offering visibility into energy generation, consumption, and storage. Dynamic control. It can dispatch resources instantly to respond to grid demands, such as frequency regulation, load balancing, or peak shaving. Rapid response. With advanced algorithms, the EMS enables VPPs to react promptly to fluctuations in energy supply and demand, ensuring stability and reliability. A virtual power plant VPP is a network of decentralized power generating units, such as solar panels, wind turbines, and battery storage systems, which are integrated and controlled by a central software system. This setup enables the combined power resources to be managed as a single entity, providing reliable and efficient energy to the grid. VPPs can optimize the balance between energy supply and demand, support renewable energy integration, and enhance grid stability by coordinating distributed energy resources. Essentially, they transform small, individual power producers into a formidable collective force in the energy market.